Hello, we're going to continue with our videos on ordinary differential equations in this video. The example that I'm going to give you is not, on this occasion, a non-linear ordinary differential equation, but it is a second order linear ordinary differential equation, but with one of the coefficients that is not constant, something that is a variable coefficient. So I'll write the equation down that we're going to look at, and the equation is y double prime minus x y prime plus y equals 0, and we'll call that equation 1. In fact, I'm going to write it a little bit closer to the left hand side, and then I can conserve space. So once again, that's y double prime minus x y prime plus y equals 0. And let me divide the board in two. So that's our equation 1. Okay, so how are we going to solve this? Because normally these types of equations with non-constant variable coefficients are generally not that easy to solve, and the more complex these equations become, the more difficult they are to solve, and sometimes it isn't always possible to solve them, at least not unless you use numerical methods or series solution methods. But in this case, we can solve this equation, but we have to use a bit of trial and error to start with to find the first linearly independent solution. So what are we going to start with? The simplest answer would be to start with a constant. See if that works. No point starting way up at the other end of the scale and trying to find something really complex. If a simple constant or some kind of linear relationship will solve this equation and equate the left hand side to 0, because that's what we want to prove. We want to prove that LHS, the left hand side, is equal to 0 for at least one linearly independent solution. And we have to find that first linearly independent solution. So let's make a start. I'm going to suggest that one linearly independent solution is just C, which might be positive, which might be negative, but anyway, we'll call it C. Now, what we're going to do is we're going to differentiate y equals c twice, because we want to substitute the second derivative into there, the first derivative into y prime, and then we just want to substitute y equals c in for y. So the second derivative into y double prime, the first derivative into y prime, and y equals c just in for y. Well, if we differentiate y equals c, we get y prime equals 0. The derivative of a constant is always 0, whatever the derivative is. And of course, the second derivative of y is just 0 as well. The derivative of 0 is just 0. So if we substitute 0 in for y double prime up here, 0 in for y prime, and c in for y, we can try and find out if this left hand side is equal to 0. So the left hand side is equal to 0, so that becomes 0, minus x times, we'll put 0 in brackets, plus c. But as you can tell, that is equal to c, which is not 0. necessarily. C might be 0, but in this case, it's just the constant letter C, which is not 0. We want something which cancels out nicely on the left-hand side to give 0 on the right. So, y equals C is not a solution. So let's try something else. Now, as it happens, there are two solutions. Two first linearly independent solutions for this. One of them is a constant times x, but we're going to prove that this works. And the other is y equals minus cx. But what we're going to do is we're just going to deal with the positive version of this for now. But we can say that minus infinity is less than or equal to c, which is less than or equal to infinity. So c takes any negative or positive value. So that's how we can just get away with using the one linearly independent solution, which yet we have to prove. So y prime is equal to c, just c basically, because x differentiates to 1 and y double prime differentiates to 0. And to prove that this is a solution, we substitute, once again, like we did with the constant, we substitute y double prime equals 0 there, y prime equals c, and y equals cx. So what we have is the left-hand side is, well, we'll write this equation out again. Y double prime minus x y prime plus y. We're not putting the 0 on there at the moment. So this is equal to 0 or 0 for y double prime minus x times c for the y prime bit plus cx. And if we work this out algebraically, then we find that it is indeed equal to 0. So we can make the assertion that y equals cx is a solution, is one linearly independent solution to equation 1 up here. What I'm going to do now to save space is to rub this working out below here, just on the lower half, and relabel this equation here, y equals cx, as equation 2. Because I'm really trying to conserve space. So hopefully you've got that down. There we are. So we'll call this equation 2. Right, okay, so we've got our first linearly independent solution. We know that that and all its derivatives, which when substituted back into equation 1, does indeed equal 0 on the right-hand side. What about the second linearly independent solution? Well, that would be a lot more complicated to deduce via trial and error. In fact, it would be really rather difficult. It certainly would for me anyway. But there is a way around this. Now that we've got the first linearly independent solution, we can use the principle of the Wronskian method. We can use the Wronskian method to find out and work out what the second linearly independent solution is. And when we use the Wronskian, we use a determinant method and an exponential method. And we've sort of hit upon a similar exponential method in previous videos. And that's the one we're going to start with. So if we let the Wronskian equal to e to the minus of the integral, if I can get this right, the Wronskian is equal to e to the power minus the integral of p dx, right? But what is p? Well, it's quite simple in this case because p is equal, there we are, there's the equal sign, p is equal to minus x. So, we quite simply substitute, I'll write it up here and then we conserve a bit of space, e to the minus times the integral of minus x dx. So we've got double, the Wronskian is equal to e to the power of the integral of x dx, right? So what do we get if we integrate x dx? Well, we get e to the x squared over 2. And that is part of our Wronskian now. The second method is to write the Wronskian as a determinant kind of matrix. It's sort of a matrix, but it's one where you actually take the determinant. So we've got y1 here, and we'll write down y prime. y2 is the unknown solution. Sorry, y2, y sub 2 is the unknown solution that we have to find. And then here we've got y2 prime. And you probably may know this, but the determinant is just y1 times y2 prime minus y2 y1 prime. That is the determinant. So how do we know what y1 and y1 prime is and y2 and y2 prime? Well, we know what y1 is because we've got it up here. We can rewrite y1 equal to cx, and of course we can now work out what y1 prime is. So y1 prime is just c. So the Wronskian in this case is equal to, well, y1 is just cx, y1 prime is just c, but we leave the y2 and the y2 prime alone, and we just calculate the determinant of that. So what we've got, if we substitute these values here into here, or just work it out straight off from the algebra in the on the board, then we've got cx. Let me write that a little bit clearer. I'm going to rub this out and just make it a little bit more brief. There we are. So we've got y1, which is cx, c, y2, y2 prime. So I've written it a little bit more compact so it doesn't take up as much space. And that's equal to cx times y2 prime minus cy2. And we'll just write that down there. Now this is actually a first order differential equation, because y2 prime is actually dy2 by dx as a differential, as a derivative, if you like. So we can actually replace this y2 prime by dy2 by dx minus everything else just stays the same. And of course this, and really I should be labelling these equations So this is equation 3 and this is equation 4. So if we equate equation 3 and equation 4, we get cx dy2 by dx minus cy2 equal to this, e to the x squared over 2. Let me write that more neatly. E to the x squared over 2. And we'll call that equation 5. Yeah. Right, so how do we solve this? Well, those of you who've studied high school mathematics will very possibly recognise how to solve this left-hand side, but we really need to simplify it first. So if we divide through by cx, we obtain, and I'm going to write it up here, but I'll write it in green, we obtain dy2 over dx minus, well, the c's cancel when you divide by cx, and you get 1 over x y2, and that is equal to, we'll call this c3 because we're dividing by a cx there, we're dividing by a cx there, so I'm just calling the 1 over c3, and we've got an x, and the e to the x squared over 2 stays the same. Right, so to solve this equation, as I said, from high school mathematics, you might recognise that to solve this equation, we need to find an integrating factor. So the integrating factor, and I'll write this in red, the integrating factor is found by finding e to the power, let me see, I want to allow myself enough room again. So the integrating factor is found by calculating e to the integral of this little bit here, minus 1 over x. So it's minus 1 over x dx, which is equal to e to the minus log x. And as I've said in previous videos, this e to the minus log x can be rewritten as e to the log x to the minus 1, which is the same as e to the log of 1 over x. And of course, the exponential raised to the power of a logarithm of a number or a function is just that number or a function. So that would be equal to just 1 over x, right? So the integrating factor is 1 over x. And of course, we've sort of got rid of the minus sign here by using this algebra. Instead of having an integrating factor of x, we've actually got an integrating factor of 1 over x. So we multiply that 1 over x by, I'm going to call this equation 6, if I can just squeeze it on. So we multiply equation 6 by 1 over x, right? So that we get 1 over x dy2 over dx minus 1 over x squared y2, which is equal to c3 over x squared, because you multiply both sides of the equation by that 1 over x, and that of course is e to the x squared over 2. Right, well, again, if you're familiar with the integrating factor method, you're familiar with how to rewrite this as a single differential or derivative on the left hand side equal to this on the right hand side. Well, there are two functions. We know one of them must be y2, which are multiplied together, and the derivative of that product is equal to this on the left hand side. As it turns out, that product is 1 over x times y2, y sub 2. Right, d by dx. Okay, because, and I'll just quickly run through this, when you differentiate the y2, the y sub 2, the 1 over x stays the same. So you've got d 1 over x dy2 by dx, and this of course is actually, let's just write that a little bit more clearly. You'd normally write that like that. That bit in brackets, in parentheses, is actually x to the minus 1 y2. So then, after you've differentiated the y2 and left the x to the minus 1 alone, you then differentiate the x to the minus 1 and leave the y sub 2 alone. So if you differentiate x to the minus 1, you just get minus 1 over x squared y2. And that, of course, is exactly what we've got here on this line above. 1 over x dy sub 2 by dx minus 1 over x squared y sub 2 equals c3 over x squared, all times e to the x squared over 2. And of course, this is the more compact form of what is on the left hand side. So we'll just erase that little bit of scribbling, a little bit of rough working. Let me just put the bracket back around that. So this is what we've got on the left hand side, and that is equal to c3 over x squared e to the x squared over x squared over 2. Now, we're not finished yet, because what we have to do is integrate both sides. So if we integrate both sides, we're just left with this on the left hand side, which is 1 over x y2, and that is equal to, I'm going to take the c3 outside the integral sign and make that integral sign look a little less skewy. So we've got 1 over x squared e to the x squared over 2. Right. Now what I'm going to do is I'm going to attempt to integrate the part on the right hand side. And actually what you get if you do that is, and I'll write it in green, I think. So we've got 1 over x y sub 2 equals c3, because you have to integrate this by parts, by the way, if I didn't already say that. So we're integrating this by parts, and if you do that, you get c3 e to the x squared over 2 and in fact there's an x in that as well. So then we have a minus sign, C3 times the integral of e to the x squared over 2, and that is all multiplied by dx. We still have a bit of a problem because we've got an integral of an e to the x squared over 2 there, and there is no easy way of integrating that. In fact, you can't integrate it, but you can approximate it numerically. Now, what e to the x squared over 2 is actually, what the integral of e to the x squared over 2 actually is the following, and I'll write this whole equation out. I'm just going to write that as y2 over x there equals c3 over x e to the x squared over 2. If I can write it more neatly, and we're minus c3, the root, so the square root of pi over 2 times the imaginary error function, and so that would be x over root 2. Now, I'm not going to go into what the imaginary function is or how we get there. That is just a fact that integral is equal to this here, and as I said, it's the imaginary error function. Now we're almost there with the second solution, because if I just rub this side of the board out, all right. I'll go back to using black pen now. So if we multiply, I can't fit an equation number onto that, but we could call it 7. We'll just say multiply through by x to get, we'll say to obtain y2 equal to c3 e to the x squared over 2 minus c3, the root of pi over 2 times, times x times the imaginary error function of x over the root of 2. Okay? And that is a second solution. Now, we know that a general solution is y equals y1 plus y2, where y1 equals cx. Yeah, so what do? Well, we just add that to that. Thus, y is equal to Cx plus C3 e to the x squared over 2 minus C3 times the square root of pi over 2 x times the imaginary error function x over root 2. Right? And that is our solution. That is our general solution. So let me just cordon that off. And that is how you solve this type of equation. So you have to use a bit of trial and error to start with. It might not even be possible to do that for some of these types of equations. You know, you might have to resort to a computer which will at least have a go at finding an analytic solution like this for some of these types that really doesn't give an obvious and linearly independent solution to start with. But there might be one, but it might be complex in itself, complicated. So obviously that's where computers come in. And if the computer can't do it, and you certainly can't do it, then there are numerical methods and series method solutions to solve these types of equations. And of course you could have used series solutions to find a general solution to equation 1. So I hope that's been okay for you and that you've learned something, and that you will be coming back for future videos, or indeed past ones if you haven't seen those. So until my next video, I'll bid you farewell for now, and until then, see you later.